Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Houston, we don't have a problem. Today we want to begin a new whole brand new chapter in the world of physics. And that has to do with electric fields, electric charge, electricity. Very different than the things we've been learning about with waves and kinematics. We have a lot of really cool stuff to learn. So let's talk about like the history of like electric stuff. Now you probably remember the famous experiment of Benjamin Franklin and lightning. You've probably seen videos about that. And so electricity's been known for a long time, way before Benjamin Franklin. In fact, back in like, 600 BC, they discovered that amber's sort of cool because like fossils are found in amber. And if you take that amber, that it can attract like things, that there's a charge to it. In fact, let's do a cool experiment that I want you to repeat at home right now. So electric charge. I want you to do this at home, right? I've got a file, right? This is a file that has a plastic end on it. Actually, a better device for you to use is a plastic ruler, but Mr. Bergmann does not have a plastic ruler at home. And a wool blanket. So I have a wool blanket, and I'm going to strip the electrons away from the plastic part. Notice I'm holding the metal end. And then when I take it down and put it close to these pieces of paper, notice what happens. See how they attracted to it? What's happened is the electric charge of the device here, of the file thing, is evident. So we have electric charge. Let's do one more thing, though. I want you to do at home as well. Next up, we're going to take your faucet, and you'll need to get just a small trickle of water. Small trickle of water. Rub this. Let me get the small trickle of water going. Just like as small as you can possibly get. Now watch what happens when I rub this. Again, I want you to do this at home. Take a video of it. Watch what happens. See how this is bending the water? See, water is polar. Remember back to chemistry class. And the polarity of the water, it's bent because now we have a negative charge on the plastic end of the file thing. So that's pretty cool. Now I want you really, if you have not paused and done that experiment, I want you to do it and shoot me a video of doing it. But let's talk about what's going on with rubbing the plastic, right? Because when we talk about electric charge, if you think about the word electric charge, it comes from a word. Well, actually, the other word came from it, but a word that you've seen probably in the previous class that you took, possibly chemistry class, and is the word electron. And if you recall from your world of chemistry that electrons have a negative charge. Also, by the way, there are protons, right? And they have a positive charge. So that's important because what I was doing, because that plastic thing was made of protons, neutrons, and electrons. Neutrons have no charge, and so they don't apply here. And what I'm doing is I'm actually stripping away the electrons and transferring them actually to the wool. So if I've got the charged rod, right? And what's happening, if you strip away the electrons, think about that for a moment, it gets a positive charge. And then the paper, the bits of paper, which by the way are neutral, right? They somehow are attracted to it. That was also true, by the way, for the stream of water, right? If I had the stream of water, which is neutral, but water's polar. This is water, right? It's polar. If you remember, that means it has a positive and negative side. That also was attractive. By the way, it's attractive on both sides. Whether I put the rod on the left or the right, it attracted it, didn't it? And that has to do with the nature of the loose bonds that hold water together. If you think of a stream of water filled with positives and negatives and negatives and positives, what happens is, maybe you know this from like ever, kind of a general rule is that positive things are attracted to negative things. And positive things are repelled by positive things. So if a positive part of the water molecule is on this side, it's going to move, it's going to repel and go over on this side. And what that's going to do, it's going to leave the negative side. So it's going to kind of go like this. And then what's going to happen is the positives are going to attract the negatives, and then the water stream is going to move over. And the same thing is happening, by the way, here with the piece of paper. So make sure you can explain why the pieces of paper or the stream of water are attracted to the rod that you did, right? You did in your class. So where does electric charge come from? It comes from electrons, all right? Or moving electrons from one thing to the next. You may say, why can't I just move protons? Again, it gets down to the structure of the atom. If you recall back to previous science classes, the nucleus of an atom has protons, I'll say P positives, and neutrons in them in zeros. And way on the outside are the electrons. So the only thing you can really move and strip, you can make something positive, but that's by taking away the negative electrons. Or you can add electrons, and that makes it positive. In fact, this is how lightning works. It's quite an important thing. So electric charge is basically we give something a charge by stripping or adding electrons to it, and now it's charged. Make sense? Now, we measure electric charge. Chemistry class, we're in a physics class after all. We like to quantify everything. And we measure electric charge with a new unit, a unit we've never seen, a fundamental unit, and it's the charge of an electron. So the charge of an electron, C-H-A-R-G, of one electron, just one little itty-bitty electron, is a tiny number, 1.6 times 10 to the minus 19th. And now we have a brand new unit, a C. Now a C is the term for a coulomb, C-O-U-L-U-M-B, named after this guy. So it's a coulomb, it's a capital C, that's the charge of one electron. So by the way, that's the charge of one electron, and one electron has a negative charge. The charge of, by the way, one proton is the same number and positive. If I had two of them, it would be double, 3. But we don't work in 1 and 2 and 3 electrons. We're going to work in moles and moles of electrons. Again, that's a term maybe you learned from chemistry, but many electrons. So we can get charges where we get lots of coulombs because electrons are so small, but you get enough of them with a charge, then this is how we measure electric charge. So as we discuss this, I want to just kick out 3 new terms, and maybe you've even heard these. The term conductor. So some substances are conductors, and that's ones that can conduct electric current or electric charge. Okay, they tend to be metals, all right? And that's because electrons, that's E minus is electrons, are free to move through those substances, and metals can do this. That's why you don't take like a metal nail and stick it into an electrical socket. That's really a bad idea, right? It'll kill you. All right, then there are the opposite of a conductor called an insulator. And an insulator is something that doesn't conduct electricity. It comes down to the structure of the atoms inside of them, and it doesn't allow the electrons to move freely from atom to atom. So actually plastic is a good conductor. Insulator, or rubber is even better. Now we can still strip a little bit off it, but really electrons can't travel back and forth in there in any appreciable way. And then there's one that's kind of a weird one called a semiconductor. And this is one that's in between the two, that's both conductor and insulator. So some can conduct, some electrons can move, and some, but not as many. And semiconductors, why is that important? You're watching this on a cell phone, which is basically a computer. You're watching on your computer, and they're using silicon. Silicon is the main sort of semiconductor of the world. They're using silicon chips, and the chips are semiconductors, and the fact that you can have that makes a huge difference in how computers and stuff work. I mean, I didn't say this at the top of the game, but electric charge leads us to electricity. Electricity leads us to our modern world. This is one of the most amazing things, that we are able to harness the power of electricity, of electrons, to do so many things, right? To light the lights that are above my head that you can't see, to power your cell phone, and to power your car if you have an electric car, or even the radio, or anything that's electrical. We've become so dependent upon how we've harnessed these crazy electrons to do super cool stuff, which is sort of the big point of what we're going to get to in the next units. But this is the introduction to this thing called electric charge, and we're really talking about something that's a little bit called static electricity as opposed to sort of current electricity. Coming up later, we're going to get all that stuff and dive in deep. Again, I want to tell you this. Make sure you go do these experiments. Let's do one example before we finish. So let's do this example right here, right? Find the amount of the positive electric charge in 1 mole of helium atoms. Hint, the nucleus consists of 2 protons and 2 electrons. And so, now moles. This is going to be a little bit tricky, but you're going to say you have 1 mole, right? 1 mole of helium atoms. I'll say helium atoms. This is going to be just kind of a big, what do you call it, railroad track problem. Now you might remember 1 mole of anything, of helium in this case, is 6.02 times 10 to 23rd atoms, right? And the moles of helium atoms cancel. And then I can say I've got atoms, and I can say there are 2 protons in every 1 helium atom, right? The atoms cancel. And now I've got one last factor. This is the new number we've been looking at, right? We can say there's 1.6 times 10 to the minus, was it 19th? Yeah, 19th coulomb for every 1 proton. That's the number we had earlier. Now we get our calculator out. We take 1, that's easy, times 6.02 times 10 to the 23rd, times 2 times 1.6 times 10 to the minus 9th. And by the way, this is going to give us an answer in coulombs. And we get 1.93 times 10 to the 5th coulomb. So if you have 1 mole of helium atoms, you have this much positive charge inside the nucleus of the atom. By the way, you have that same charge of electrons that balance each other out. Houston, we've got no problems. We'll see you in class.